Okay, but I'm going to go ahead and go over this example now. Find the probability of randomly selecting a person, or let's see, no. Find probability a randomly selected person will be Democrat or Republican, okay. So this is or is associated with the and rule. So here I go. So I want the probability of them being a Democrat or a Republican. So this will be D and this will be R. And so that is going to equal, so I've got to compute the total here because I need to divide by the total. So I'm going to add it all up. So 437 plus 433 plus 188 plus 43 equals, so this is 1,101. And now the other, among the 50 or below, I get 301 plus 427 plus 140 plus 129. Okay, and I add that up and I get 1,007. And I add both of those together, I get 2,108. Okay, so the probability of being a Democrat or a Republican is going to be 437. So that's the so how many? So this is the set I'm looking for right there. How many are in that set? Well, there's to the best of my knowledge, there's nobody who's a Democrat and a Republican at the same time, and so we'll go 437 plus 433. And so then we divide by 2,108. And so that's the probability of that. And what is that exactly? That's 437 plus 433. That divided by 2,108 equals, so that's about 0.413. So about 41.3%. All right, great. Now, find the probability of randomly selecting a person. Find probability a randomly selected person will be a Democrat or 50 or below. Oh, wait a minute. Now, okay, so for some reason I assumed that they had to be over 50. So if I want to get this, I need to add these people in as well. So let me just fix that. So we've got, okay, so clear this. So 437 plus 311 plus 433, well, let's see, plus 427 equals, okay, so this is 1,600 there. Okay, now 1,608 divided by 2,108 equals 76. Okay, so this is 0.7, so this is approximately 0.763, and so the probability of somebody being a Republican or a Democrat is going to be, given this data, is going to be 76.3%. All right, great. Now, what's the probability of randomly selecting a person who is a Democrat or somebody who's over 50? All right, well, we need to count, so we want to count these people and these people. So the Democrats and the Republican and the people 50 or below. But notice that 131 of those are in both categories. Now we can't count one person two times. So we're going to subtract that difference. So here we go. So we're going to do the probability of D or, let's just say B will be, so this will be B, this will be O. So that's going to be D or B, and that is going to equal, we can do this two ways, right? We could do the number of Democrats, which is 437 plus 311, and that's 748. That's the total number of Democrats, plus the total number of people who are 50 or below, which is 1,007, divided by the total number of people, 8. But what we need to do is subtract those 311 people who are double counted. Now notice this is the same thing as 748 over 2,108 divided by plus 1,007 over 2,108 minus 2,108, and that in turn is the same thing as the probability of getting a Democrat, just a Democrat, plus the probability of getting somebody who is below 50 or the age of 50 with no other considerations, just somebody who's in that age band, minus the now notice this is the probability of them being a Democrat and below 50 or below. And so that's what we get. And so, well, what is that? Let's see. So 478 divided by 2108 equals, okay, so this one here is going to be 0.355 plus 1007 divided by 2108, and that equals 478 minus now 311 divided by 210, like that. And so that's going to be 0.148. And that is going to end up equaling 0.355 plus 0.478 minus 0.148. See, did I get all that in there okay? Yeah, I think I did. And that equals 0.685. And so the probability there is going to be 68.5%. Okay, great. So there's that example. All right, so moving on. When it's on a white slide, I'm going to look for these things being filled in if you want full credit on the slides here. But you don't need to fill in anything on these example slides. That's just a bonus if you want to. Okay, let's take an example here. Go back to our screening, the drug test. So, so there it is. Here's the setup. Okay, 50 test results from the subjects who it was shown to be that right there. Okay, so continue with this example. If 2 of these 50 subjects are randomly selected with replacement, okay, with replacement, so that means it's an independent trial, find the probability the first selected person has a positive test result and the second selected person has a negative test result. All right, so 2 out of these 50, so these are drug users, okay, so they do use drugs. What's the probability that when we randomly select 2, that the first is positive and the second one is negative? Okay, so that's going to be the probability. Is with replacement. So event A is going to be first person, let's see, the first person selected was a positive test result, positive. And B, second person, negative. So we want to know what the probability of both of those things and. All right, so this is going to be the probability of A and B. Now, because it is with replacement, whoever was selected in A is just going to be put back into the mix. And so whatever A was, it does not affect what B was. And so I use my multiplication rule. This is the probability of A times the probability of B, given that A has occurred. However, the probability of B given A occurs is the probability of B, because it does not matter what A was. The probability of B will be the same. And so this right here is the probability of A times the probability of B. And we already knew that because these things are independent. Okay, now here's the more tricky part. Repeat part A, assuming that the two subjects are selected without replacement. So we're not putting them back. All right, so here's what we do then. So this is going to be the probability of A and B. Now this is without replacement though. So this is going to be the probability of A times the probability of B given that A has occurred. Okay, now the probability of A, which is that we find somebody who tested positive. Well, how many people tested positive among the 50? 45. So that's going to be 45 over 50. Now watch carefully. The probability of getting B given that A has occurred. Now if A has occurred, how many people are there left to choose from? 49, because A has occurred, and that person that was chosen was taken out of the pool. Now, because it was A that occurred, the person that was taken was not a drug user. And so the probability, so there are still five drug users in that pool of now 49. And so this is going to be 5 out of 49. And that's our probability. Now, what is it? Let's just punch it in my calculator here. 45 over 50 times 5 over 49 equals 9. And let's see, and that equals 0.092, or about 9.2%. Okay, now I didn't actually finish this one right here. So this is going to be, so for this one, the probability of the first person having a positive test result, well, that's 45 out of 50. And the probability of the second person having a positive test result is 5 out of 50. Because remember, this is with replacement. So whoever was randomly selected out of the first poll is replaced, and there are now 50 subjects again. Okay, and so what is that? That's going to be 45 times 5 divided by 2500, and that gives me 0.09. Okay, which is 9%. Okay, great. All right, here's an example. Assume that 3 adults are randomly selected. Well, this is without replacement. Of course, we don't want to survey the same one person 3 times. And it's without replacement from this, which is the total amount, which is the total adults in the United States. Okay, assume that 10% of adults in the United States use drugs. Find the probability that the 3 selected adults all use drugs. All right, so we've got three different trials that are strictly speaking not independent. However, the sample size is 3. I'm taking 3 out. And the population is much bigger than 5, 3 is much smaller than 5% of the population. See, so remember, if we multiply that by 3, we get 60. And so the population would have to be bigger than 60 in order for 3 to be less than 5%. Well, it's way bigger than 60, so we're perfectly fine to do this. And so what we'll do is A is going to be the first selection. B is going to be the second selection. And C is going to be the third selection. And so the probability, so I want the probability of, first selection user is a user. The second selection is also a user, and the third selection is a user. So I want A and B and also C. I want all 3 of those to be true together. And so that is going to equal the probability. Now, because of the cumbersome calculation rule, I can assume that each of these are independent. And so that means that that's just going to equal the probability of A times the probability of B times the probability of C. All 3 of those are independent. And what is that? Well, that's going to be this 1/10. So that's going to be 0.1 times 0.1 times 0.1. And that's going to equal 0.001, or about 0.1%, 0.1%. Okay, and that's using the cumbersome calculation rule. They are independent. Not really, but it's okay to do that. Okay, now here's an example. Modern aircraft are now highly reliable, and one design feature contributing to that reliability is the use of redundancy, whereby critical components are duplicated so that if one fails, the other will work. For example, the Airbus 310 twin-engine airliner has 3 independent hydraulic systems. 3 independent hydraulic systems. So if one system fails, full flight control is maintained for another with another functioning system. All right, so for this example, we will assume that in a typical flight, the probability of a hydraulic system failing is 0.002, so 0.2%. If the Airbus 3 were to have one hydraulic system, just one hydraulic system, right? What's the probability that the aircraft's flight control would work for a flight? Okay, so we're saying what's the probability that it will work, and so that is going to be, this is a complement here, right? So it's going to be the probability that it works is going to be 1 minus probability that it doesn't work and the probability that it doesn't work we know to be 0.2% or 0.002, and so we get 0.998, which is 99.8%. So that's the probability that it will work. Given that the Airbus 310 actually has 3 independent hydraulic systems, what is the probability that on a typical flight control can be maintained with a working hydraulic system? Okay, so P that at least one works. And so we've got at least one works. Now that is going to be the same thing. That's going to, so what's the opposite of at least one? So at least one means one or more. The opposite of that is none. So that's going to be 1 minus the probability that none work. And the probability that none work is the probability that all three have failed. Now these are independent systems, so let's see now. So the probability that none work is the probability that first failed and second failed and third failed. And so that's going to equal the probability, because these are independent, that's going to be first failed times probability that second failed times probability that third failed. And that is going to equal 0.002 times 0.002 times 0.002. So that's 3 times. So that's going to be, let's see, so let's use scientific notation. This is, each one of these is 2 times 10 to the negative third. If I raise that to the third power, I get 8 times 10 to the negative ninth. And so the probability that at least one works is 1 minus 8 times 10 to the negative ninth. Which equals, let's see here, so this is going to be 0.9999999. Let's see, move this out of the way. 99, and then what? 2. Which is very, very close to 1, right? So this is 99.999992%. Very reliable. Very, very reliable. Okay, now here's an example. A study by Square Trade found that 6% of damaged iPads were damaged by bags or backpacks. If 20 damaged iPads are randomly selected, find the probability of getting at least one that was damaged in a bag or backpack. Is the probability high enough so that we can be reasonably sure of getting at least one iPad damaged in a bag or backpack? So the idea here is that you've got a person and they work at this refurbishing company, and they've got a whole warehouse full of iPads that were damaged because of bags or backpacks. Let's say it's over 2,000, so we can use the cumbersome calculation rule here. It doesn't tell us how much. I'm assuming that this would be done without replacement. And so I think the intent here is to employ the cumbersome calculation rule because we're looking at 20. All right, so okay, so here we go. So we want to get at least one that's damaged by bags or backpacks. So this is the probability of at least one, and I'll call it bags, backpacks. Okay, so that's the same thing as the probability of 1 minus the probability that none are bags, backpacks. That none are bags, backpacks. So that is 1 minus the probability that the first is not bags and backpacks times the probability that the second is not bags and backpacks, all the way to the probability that the 20th is not bags and backpacks. Now, again, we're employing the cumbersome calculation rule, assuming that the total number of iPads is bigger than 400. Remember, that's 20 times the sample size. So if the total is bigger than 400, we can use the cumbersome calculation rule, which is what we would like to do, and assume that all of these are independent, which is what I'm doing. Okay, now what's the probability that a single a single selection is better? A single selection is not bags or backpacks. Well, that is going to be 94%. That's 1 minus the probability that it is. So that's 94% or 0.94. So this equals 1, this thing here. Equals 1 minus 0.94 raised to the 20th power. I multiplied that 20 times. And so what do I end up getting? 1 minus 0.94. I need to get my scientific calculator out. 0.94 to the 20th equals 0.70 0.710 or 71%. So 71%. So roughly two chances in 3 that we will get is the probability high enough so that we can be reasonably sure of getting at least one iPad that's been damaged by bags or backpacks? I would say probably not. I don't know. 71%. Is it enough? No. I'd like to have more certainty than that. Okay, so 70% is really not all that much. Okay. Great. So let's go on. Okay, now there's a solution. Cumbersome calculation rule. Yes, we did it. Another example. Subjects for a public opinion poll on a particular city park are contacted by telephone numbers in which at least 4 digits of randomly selected with replacement, Find the probability that one such number that in one such number the last 4 digits will have at least 1 0. Okay, so probability at least 1 0. That equals the probability, so that equals 1 minus the probability of no 0. And so that equals 1 minus the probability that the first of the 4 digits not 0, and the second not 0, and third not 0, and fourth not 0. Whole bunch of ands. These are all, they're independent of each other because it's without replacement. Because it's with replacement. And so this is going to be 1 minus the probability of first not 0. Probability that all the way to the fourth not 0. That equals 1 minus, now the probability that the first one's not 0 is going to be 9 in 10. There's 9 digits. There's 10 total digits, counting 0. And there's 9 that are non-zero. So 9 and 10 minus 9 and 10 times 9 and 10 times 9 and 10. This is for each one of these. All right, and so we end up getting 1 minus so that's 1 minus 0.9 to the, where's my scientific calculator? 0.9, 0.9, 4 times 30, so that equals, let's see, did I do the, one minus 0.9 times 0.9 times 0.9. Okay, so 0.9 to the fourth equals 0.344 or 34.4%. So find the following using the table. If one of the 555 test subjects is randomly selected, find the probability that the subject has the positive test result, given that the subject usually actually uses drugs. That is, find the probability of a positive test result. Find the probability of a positive test result given the subject uses drugs. All right, so if they use drugs, they're going to be right here among these. So that's 50. And then a positive test result is 45. So the probability of positive, given they're a user, is going to be 45 out of 50. Now let's use the formula for that. So P of a positive test result, given that they're a user, is going to be the probability that you have a positive test result and you're a user. And that is, that's the 45 divided by the probability of being a user. And so this one here is going to be 45 out of 555 divided by probability of being a user, 50 over 555. And we simplify, we end up getting 45 over 50. I'm going to go ahead and skip this one. Okay, let's just do this one last thing. All right, so here's an example. Assume cancer has a prevalence of 1%, meaning that 1% of the population has cancer. Denote the event of having cancer by C. Denoting the event of having cancer by C, we have P of C equals 0.01 for a subject randomly selected from the population. Okay, so now so interpreting a medical test here, the result is included with the following performance characteristics of the test for cancer. So the probability of there being cancer is this. That's the prevalence rate. The false positive rate is 10%. That is testing positive given that cancer is not present is 10%. The true positive rate is 80%. So positive given that cancer does occur is 80%. Now what we want to do, notice this one was not given. The probability of having cancer given a positive test result. So you have a positive test result. A lot of people seem to think that that means that you have cancer, but it's not necessarily the case. So what's the probability that you actually do have cancer given a positive test result? We can determine that. Find the probability. Yeah, all right. So here's what we're going to do. We are going to sort of do a little thought experiment here. We're going to compute. We're going to make a table here. And so this is going to be, so here we're going to have has cancer, sort of a hypothetical study. This will help us. This will greatly facilitate our being able to answer this problem. So this one here is has cancer. This one here does not have cancer. This is going to be the total. Now the total in our hypothetical study, I want to be 1,000. Now just a big number, 1,000. Big number that's easy to work with. 1,000. Now, according to the prevalence statistic, 1 in 100 have cancer. So if there were 1,000, the total that have cancer would be 10. And the remaining would be 9,990. Okay, now the false positive rate is 10%. So that means that, okay, and this right here is test positive, test positive, test negative. All right, and so the false positive rate, the false positive rate, that's a positive test, given that cancer is not present, is 10%. So 10%, so given that it is not positive, so this is my total here, is 10%. So that means that that I need to take 10% of this, and 10% of that is going to be 999. Now I just do a little Sudoku action here. If that's how many have a positive test result, what goes here just needs to add up to that. And so I take 9990 and I subtract 999 and I end up getting 8991. All right, now I also know that the true positive rate, the probability that you test positive test given that cancer is present, is 0.8. And so that means there's going to be 8 right here, because 0.8 times this total, when we know that cancer is given, is 8. And so this must be 2. And so that gives us our total. Now, we wanted the probability of cancer given a positive test result. So what's that going to be? Well, if given, I add up these right here. So 999 plus 8 is 1007. And the probability of actually having cancer given that is 8. And so my false positive, no, and so I get 8 over 1007, and that's going to be 0.00794 or 0.794%.